So, so a lot of these will follow a pattern. There's a very common pattern that is easy to recognize. Um, so if we have iron 3 sulfide, and so sulfide is a 2, iron is a 3, so it's going to be Fe2S3. Sulfides are all insoluble except for group 1 ammonium and group 2, so this is going to be a solid. And then acetic acid. Acetic acid, there are different ways you could write acetic acid, but probably the most common way people write it is HC2H3O2. And acetic acid is going to be aqueous, so as I said before, I'm not going to write aqueous on here. Now, the pattern that you can see here is it's going to be an AB plus a CD type pattern. This is labeled a double replacement pattern. And so what we do here is, I like to do this. I like to just swap the anions. So rather than having an AB, I'm going to make an AD. And rather than having a CD, I'm going to make a CB. So I just swap the anions. So we just look at what is the cation. The cation is iron 3, but I'm going to use the other anion. The other anion is acetate. And so I will just go with here, iron 3 acetate. Now iron 3 is a +3, acetate's a -1, so we're going to need 3 acetates to balance the charge. And so this would be one of the products. The other product is going to be the H+ cation with the sulfide anion. Now sulfide is a -2 and hydrogen is a +1. So to balance out the charge, we're going to need 2 of the +1 hydrogens for every -2 sulfide. And so it'd be H2S. Would be a second. So AB yields, what we're going to have here is AD plus CB. And so this is how I figure out what the products are. If it fits this format, and this is called the double replacement format, which is probably the most common metathesis type reaction here. Now, when you're first learning reactions, you just want to see if they fit some kind of pattern that you can recognize. As you start to do more and more of these, then you aren't going to be as restricted to it. So, for example, if it doesn't fit a certain pattern, you still can probably figure it out, based on what you know about the other stuff. But it's not balanced. But before I balance it, I want to make sure that there's a driving force. And so, is iron 3 acetate going to precipitate? It will precipitate if it's an insoluble solid. But we know that acetates, nitrates, and chlorates are all soluble. And so this is not going to precipitate. Hydrogen sulfide's a gas. And so we're generating a gas here. It's a toxic gas. So one thing is, H2S is also somewhat soluble in water. And so what we could write here is, it's either going to be a gas or aqueous. How do you know it's a gas? This is part of the memorization stuff. The part of the memorization stuff is you would know hydrogen sulfide is the rotten egg odor that eggs give off. And so that is a gas because you can smell it. There's also bacteria that produce hydrogen sulfide in volcanic vents. If you go to hot springs have that hydrogen sulfide smell. It's a gas, so it... Well, the problem with the hydrogen sulfide is the odor is recognizable at the part per billion level, but what happens is it quickly desensitizes your receptors in your nose, so you stop smelling it. And it's also toxic at the part per billion level. So in Ventura, one of the workers at one of the oil fields ended up dying from hydrogen sulfide poisoning. So as soon as you smell it, you should vacate the area. If we smell it in the lab, we leave the lab, if it's strong. And so there's certain things you just memorize. And these are the gas formers. These are the common gas formers. So the common gas formers you have to memorize. So, for example, a lot of people don't memorize this, but carbonic acid decomposes, but about 10%, I'd say, typically in 1A and 1B, leave it as carbonic acid. We shouldn't leave it as carbonic acid. It decomposes into CO2 and water. Sulfurous acid is less common, but this also decomposes into sulfur dioxide and water. Sulfur dioxide is a gas. Ammonium hydroxide is much more common. And so, 1, 3, 4 and 5. 4 and 5 are just for safety purposes. You never mix acid with sulfides. If you mix acids with sulfides, you're going to, unintentionally, you never unintentionally mix acid with sulfide because H plus and sulfide make toxic hydrogen sulfide gas. And the same thing, you never mix acid with cyanide. This is one of the safety rules in lab. We don't do that because you're going to generate hydrogen cyanide, which is a gas, and that's a very toxic gas. There are others, but these ones people typically memorize. I know there's a big push against memorization, but we have to memorize certain things just for general safety and also just for general knowledge. And so I know a lot of people disdain memorization, but it's important to have certain things memorized. So there's no precipitate, there's gas formation, and there is, so we can say that there is a driving force, gas formation, and that gas is H2S. And we also have one other driving force. The one other driving force is we're going from a stronger acid, acetic acid, to weaker acid, hydrosulfuric acid. Now, how did I know those rankings? I didn't necessarily know those. I just look them up on a chart. So we could look these up because we have a table of Bronsted acid base strengths here. And so if I look it up, I can see acetic acid here. Now this is written in another way of writing. This is the condensed structural formula for acetic acid, CH3COOH. And we can see it's stronger than H2S, hydrosulfuric acid. Yes, you don't have to memorize this. Sometimes, you have a chart like this, but what we do is we look through the chart and look for patterns. Is there a certain pattern for strong acids, strong bases, that kind of thing. And then on the test, we might have something that's similar. This often happens. So a lot of people think, okay, this is going to be given, so I don't need to know anything about it. But if you go to a place like UC, they're going to throw something out there that you haven't seen. So, for example, here, let me go back over here. What if you have something like this? What if we had something like, as an aside here, CH3O minus? Where would you rank that? CH3O minus. So, CH3O minus is a powerful base. It's a strong base. How would you know? Actually, you would look at it structurally, because we know hydroxide is a powerful base. It's a strong base. And this is called methoxide. Methoxide is a strong base. because the electronic environment around oxygen is going to be very similar. This is what I was showing in the PowerPoint, structural analysis that we could do for this. There's very simple things we could do structurally. One is we can compare the electronegativity of hydrogen. Hydrogen's electronegativity, this is where a little bit of, where does hydrogen's electronegativity fall in terms of the periodic table? I happen to have the numbers memorized. You don't have to have the number. I have them memorized for the simple one. Well, where is hydrogen's electronegativity on the periodic table? What's it between? What's it similar to? Tell me what hydrogen's electronegativity is similar to. What elements are it most similar to in terms of electronegativity? Not fluorine. Fluorine. Not lithium. Carbon. Yeah. Hydrogen's electronegativity is very similar to carbon. In fact, hydrogen is a 2.1, carbon is a 2.5. We calculate something called delta En, which is the difference in electronegativity. The delta En for a hydrogen-carbon covalent bond is 0.4. A 0.4 electronegativity difference is considered relatively small. Therefore, we consider a carbon-hydrogen bond to be nonpolar because they're very similar to one another. When you have things that are quite different in terms of electronegativity, then it becomes increasingly polar, increasingly ionic. And so, we think of hydrogen and carbon as being quite alike in terms of electronegativity. Hydrogen is just slightly less than carbon. It fits right here. This is where hydrogen goes. It's more electronegative than boron, less electronegative than carbon. It's in the middle. This is why in some periodic tables, hydrogen is written in two places. Hydrogen is written there because it has properties similar to group 1, and it's written over here because sometimes it has properties similar to group 7, the halogens. That's on the periodic table there. And so in terms of electronegativity, we're looking at the negative charge density on the oxygen. Acid is positive, acid is H+, and so the more negative the base is, the better. And so in terms of hydroxide versus methoxide, they should be quite similar in terms of base strength. Do you see that? Because carbon and hydrogen are kind of similar. Now, although carbon's slightly more electronegative, carbon also has all those other hydrogens. And so what we call that methyl, we call it electron rich, because the different things we look at, automatically when I look at that structure, I look at formal charge. I do see formal charge on the oxygen. Do you see that? The -1 formal charge on the oxygen. But not only that, I also look at oxidation state. Now the oxidation state, can you tell me what the oxidation states are on these elements? So for example, what is the oxidation state of oxygen in hydroxide? -2. And the oxidation state of hydrogen? +1. So we have a +1 hydrogen in terms of oxidation state attached to this. If we look at the oxidation state in oxygen, what is it? -2. What's the oxidation state of carbon? Okay. +1? +1's incorrect. -2, 4, 6. Yeah, -2 is correct. So -2 on a carbon is what we consider electron rich. And this is an electron rich group. Methyl groups are electron rich. And so what that's going to do is it's going to further enrich the oxygen. The more native the oxygen is, the better it is at base. So we expect methoxide to be potentially even stronger than hydroxide because of that. Does that make sense? Well, I mean, this is part of the analysis. We'll talk about how to do oxidation states later. if you haven't encountered oxidation states in Lewis structures, a lot of people don't do oxidation states in Lewis structures. We do oxidation states in Lewis structures because we want to analyze Lewis acid-base reactivity. Okay, normally when we do oxidation states, we follow the rules, like in chapter 5 or whatever chapter that was, chapter 3. This was chapter 3, but we do it a little bit more in depth than that. So we'll come back to this, but that's part of the analysis that we'll do, structural. So you might have a chart like this, and what you do is you go through and see, does it make sense, And sometimes, it doesn't, because you don't have a clear reason. Like, for example, what's a clear reason why acetic acid's a much stronger acid than hydrosulfuric acid? No, but what we do is we try to have some reference points. Those reference points are helpful. Like when I first moved here, I didn't really have reference points because I grew up in Santa Barbara, so you have the mountains there and then you have the ocean here, and so it's easy to tell which direction you're going. But here I was like, okay, I'm going to go down to the beach. So I'm driving, I think I'm on Carson, and I'm driving and it gets longer and longer of a drive, and then pretty soon I'm way out there, on east. I was going the wrong direction, totally the wrong direction. And so what's helpful in chemistry is to have some reference points memorized, and we memorize reference points. The reference points we memorize is, what does a -2 oxidation state mean? Well, -2 oxidation state is different depending on what element you're looking at. And so for each of those elements, you kind of memorize, okay, -2 means rich for this, but not rich for that, And so all these little things we memorize, but those little things, it's not all memorization. Those little things help us make some predictions about other things that we might encounter in the future. And so we look at the range. And so, for example, do you know the range of oxidation states for carbon? What's the extreme, range for oxidation states for carbon? Yeah, -4 to +4. And that's very useful to know, because then we know, is it at the extreme end of the range or in the middle of the range, or where is it in terms of reactivity? And so I don't know. Here we just look it up in the chart, and that suffices. So we see that the acetic acid is a stronger acid based on the chart than hydrosulfuric acid. We're not going to do any structural analysis. Fortunately, it's on the chart, but at UC, they're notorious for throwing things that aren't on the chart, that aren't on the home, that weren't encountered in the homework, that kind of stuff, And so how do you prepare for something like that? Well, this is how you prepare for stuff like that.
Let's say hydrogen sulfide wasn't on the chart, would a good reference point be?
Yeah, that would be good to compare it to H2O. It would be good. Some analogous structure, and then see, because we talked about acid strength. I don't know, did you guys talk about acid strength in Chem 1A? I covered acid strength, which is the last part of chapter 16, the last 3 sections of chapter 16. No? All right. We look at what acid strength depends on. So I already spent quite a bit of time. It depends on, and that's why I just zipped through it, because I don't want to go through it completely at once. But it'll be some repetition for you guys. It doesn't hurt. More repetition, the better. That's essentially what you do in chemistry. As you progress, you already know the basic foundation. You just dig into things deeper. And so it's a lot of repetition. Of course, the problems become much harder. Yeah, so you could compare it to analogous structures like that. That would be an excellent thing to do. You'd kind of expect it to be weak, like water, although the bond is much weaker. The HS bond is much weaker than the HO bond because sulfur is so much bigger. And in valence bond theory, you'd have an sp, a gigantic sp3 orbital on sulfur overlapping with a tiny s orbital on hydrogen, versus in water, you'd have a much smaller sp3s orbital.
So hydrogen sulfide would be compared to water are stronger acid or weaker base?
The HS minus, yes, you're right. That's correct. Yeah. But on the one hand, you would predict hydrogen sulfide to be a stronger acid because of the weaker bond. On the other hand, you'd expect water to be the stronger acid because of the more polar. So there's a trade-off there, and it's hard to determine what the relative weighting is on each of those factors. So sometimes it's just hard to predict, and we would need a more quantitative quantum mechanical approach to determine that. This is why, actually, if you're continuing on to organic chemistry, you may want to get this, and you might want to start using it in 1B, and it's not that expensive. Let me tell you. You might want to get this wave function Spartan for Windows, Macintosh, Linux. They also have it for the iPad. We have an iPad. The iPad version is pretty cheap. I have the iPhone version, which isn't as powerful, but it's okay. The reason why I'm saying you might want to get this is because they offer a student price, which is really cheap. You can buy a license for this for $50. Well, it's I guess it's expensive. $50 is pretty expensive, but when you compare it with the professional license, which is like what is this per license? 7,200. Greater. This is for a single license. If your processor has more than 16 cores, 7,200. You can do these electrostatic potential maps, etc. We used to have it here, but we don't have the money for it anymore. We had licenses for our computers. But I have the iPhone version, which was like $5, I think. And still, you could do some stuff with it, so it's pretty useful to have. Especially if you're going to continue to organic chemistry. All right, so we have driving force, and so the way I label it, I just say DF, gas formation, point to it, and over here, stronger acid, the weaker acid, that's confirmed from the table. And I'll call this the driving force here for that. So there's a driving force. What I'm going to do is I'm just going to balance this. And so to balance this, we're going to need, it looks like we're going to need 3 acetates over here, so I'll put 3 acetic acids here. And then we're going to need six hydrogens. Oops. This is not quite right. This is not going to be balanced. Let me undo that. And so I'm going to erase. It's going to be, I have 2 irons here, so I'll need 2 iron 3 acetates. That's going to give me 6 acetates. So I'll need 6 acetic acids. And that gives me my 6 hydrogens, make 3 H2S. That would be balanced. So this would be the complete equation, and then I go on to the ionic equation. The ionic equation is you're going to ionize the strong acids, the strong bases, and the soluble salts. So this is an insoluble salt. Insoluble salt we leave alone. Acetic acid, is that a strong acid or a weak acid? That's a weak acid. So acetic acid's weak, leave alone. Iron 3 acetate. Is that a soluble salt or insoluble salt? Soluble. All acetates are soluble. So this is going to split up into 2 iron 3 plus. The most common error people make is they don't balance it. So they forgot to write the coefficient 2 and they forget the charge. And 6 acetates. H2S, is that a strong acid or weak acid? Weak acid, so we'll leave it alone. We'll call it a gas. All right, are there any spectators here? No. And so the ionic equation and the net ion equation are the same thing. So this is how I'd figure it out. First, usually the first thing I do is look, is it a double replacement? Double replacements are so common, AB plus CD, that would be the first thing I'd look for. All of these are double replacement except for this last one. The last one essentially is a double replacement as well. We handle that a little bit differently. All right, so what I was going to do is I'm just going to talk through the slides and then we'll work on some problems. Let's see what the schedule is today. Yeah, today I'm going to start chapter 24 as well, so let's look. Next week we're going to do some of the homework problems here, so we'll have additional time for that. All right, some things are not double replacement style patterns like this. Oh, actually, I was working on this. Was I working on this one?
Yeah.
Last time I didn't finish this one, right? All right, let me finish this one. We're looking at phosphoric acid and sodium hydroxide. We have a driving force here. This is a double replacement pattern too. It's got the AB plus CD pattern. Now, what we do with metathesis is we react it to completion. That is, we go all the way to phosphate. We don't have to. For example, we could just neutralize one of the acid hydrogens. If we neutralize just one of them, then we'll form dihydrogen phosphate. If we neutralize two of them, we'll form monohydrogen phosphate. If we neutralize all three of them, we'll form phosphate. And so what I say, react to completion, what I mean here is neutralize all of them. There are three of them, neutralize all three of them. Oh, we did the Bronsted? Oh, okay. Did we finish the Bronsted too? Yeah, with the Bronsted, we just leave it. We just react one. Later on, we're going to do it in sequence. Depends on how much hydroxide we have. So if we have additional hydroxide, we can do more. Now, there are some reactions that look like metathesis, double replacement, but in reality, they aren't going to be metathesis. So this is an example here, sodium monohydrogen phosphate. So sodium is a +1. Monohydrogen phosphate is a -2. And so we'll need 2 sodiums for every monohydrogen phosphate. And potassium hydrogen sulfate. Hydrogen sulfate is also known as bisulfate. And so this is potassium bisulfate. And so what are the ions here? Now, this is a bit different than the last one. In the last one, it was phosphate. In this one, I'm not going to go to phosphate. In this one, the ions are this. I have the sodium ion here, and then I have the monohydrogen phosphate ion here. Now, I'm not going to break off the hydrogen because, one, the reason I don't break off the hydrogen is I don't have a powerful base to take it off. Is water enough to remove a hydrogen off a weak acid completely? No. Since water is not enough to remove a hydrogen off a weak acid completely, we leave it on there. And so this is why I do not ionize it. This is why I did not ionize this. Remember H2SO4. H2SO4 I ionized into H plus and HSO4 minus. Why didn't I ionize the second one? I did not ionize the second one because water is not a strong enough base to strip that second one off. Well, the same thing happens here. Water is not a strong enough base to strip the second one off. Now, we could have other things that could strip it off, no problem. If I just have a base that's stronger than what, then I could figure it out. If I had a base that's stronger than, I don't have the acid chart here, but I could look it up on the chart. It'd be a base that's stronger than phosphate, is what I mean. All right, so here, this follows the AB plus CD. This is my A, sodium ions. This is my B, monohydrogen phosphate. And so I'm just going to go with sodium ions and bisulfate ions.
Question?
Yeah.
Is water strong enough to take off both sodium?
Yes. Water is strong enough to take off both sodiums.
So if it's in these situations, if it's something like this, if you're potassium and sodium, it's not hydrogen, we should like take them all off.
Take them all off.
Is that because they're less like ionically bonded because they're bigger?
Okay. The ionic bond is kind of strong, but the ionic bond is still somewhat weak, but the hydrated sodium ions are fairly stable. But you get to an interesting point, and that is ion pair formation. End of chapter 14. End of chapter 14, we talked about ideal solutions versus real solutions, briefly, and ion pairing. And so what happens is, this is especially important in colligative properties. For colligative properties, it depends on how many individual species there are. But if something's acting as a pair, then you just cut down by half the number of individual species. And so ion pairing like that is a problem. And so when we look at it in more detail, we will see that some sodiums kind of hang around and don't completely break off. And that's going to change something called the effective concentration of the solution activity. I don't know how much I talked about that. Have you guys heard of activity? Did you guys cover chapter 14 in your Chem 1A? All right. So the reality is, to answer your question, is we're just going to assume it's an ideal solution. We assume that it completely breaks off. Now, certain things will deviate from that behavior depending on the concentration. So, for example, the more concentrated the salt solution, the less ideal it behaves. And so it doesn't necessarily completely break off 100%. The percentage drops. If you want to, and this is something that's good to review for 1B, probably, I would, see. See if I'm still logged in. I'm not. This is pretty short. It's only 2 pages long. I would read section 14.9. So, for example, sodium chloride. Well, when sodium chloride dissolves in water, it's a strong electrolyte, and strong electrolyte should ionize 100%, correct? Well, that's only under ideal conditions. What are ideal conditions for solutions? Oops, what is this up here? Ideal is infinite dilution. Well, infinite dilution is not really realistic for us. And so as the solution becomes more concentrated, it starts to deviate from ideal behavior. Now, for Chem 1A and Chem 4, we're just not going to worry about it. We're just going to say it's a strong electrolyte. It's going to ionize 100%. So we're going to form sodium ions and chlorides. But by the time we get to 1 molar, about 10% of the ions are paired, because the effective concentration it should be 2 molars. According to colligative properties, we have 1 molar sodium ions, 1 molar chloride ions, 2 molar particles in solution. Now, because of ion pairing, the ion pairing is going to get worse as the solution gets more and more concentrated. So by the time we're at 1 molar, it's not behaving like a strong electrolyte should behave, right? There's some pairing interactions going on. And so these are illustrations of pairing actions. It's not ionically bonded, it's just ion-ion attractions. And they're paired momentarily and then they break apart, that kind of stuff. But that pairing means that they don't act individually, they act as a pair or cluster or whatever, you know. And so when we're dealing with electrolytes and solutions of species, it depends on how deep we want to look at it. For this, the chemical reactions, we're not going to look at it deep. We're just going to make a basic assumption. You know, strong electrolytes ionize 100%. Now, is that accurate? No, it's not completely accurate because of these types of pairing interactions that go on. To an extreme extent, this is why HF is such a weak acid. HF is such a weak acid because these pairs are really significant, these pairing interactions. So the H plus can't behave individually and neutralize bases, you know, kind of thing. And so 14.9, which is only 2 pages, less than 2 pages, is good to read again. Anyway, this is the type of stuff they'll ask you. Like, I remember I was, you know, teaching assistant at UCSB, and they asked a question on the Chem 1A exam there, you know, about acetic acid. You know, the predicted boiling point of the acetic acid solution was this, but the observed boiling point was that. You know, explain what's going on. And the instructor did talk about it, but the acetic acid, or actually it wasn't acetic, maybe it was benzoic acid. Can't remember. One of those. But there's such strong hydrogen bonding interactions that they ended up pairing, and they form what's called a dimer. And these pairs are quite strong. And, and so the solution, the effective concentration of the solution was quite different, and therefore I mean, it's something that was talked about in the book as well. I think it was acetic acid. There are lots of images of acetic acid dimers. You can see how the hydrogen bonding interactions pair these up, you know, especially at high concentrations.
Are there other molecules that are more than just in a pair?
Well, the classic is DNA. that forms a dimer, huge dimer, in the alpha helical structure. So that's the classic one because of the strong hydrogen bonding interactions, the pairs. The cool thing about in Spartan is you could build a DNA strand with a helical structure, and then you can turn off the hydrogen bonds. When you turn off the hydrogen bonds, it just collapses into big spaghetti noodles, basically. It's kind of cool, and then you can turn it on. Turn on the hydrogen bond, turn off the hydrogen bonding. It's like something out of science fiction. Cool. But there are trimers, etc. Yeah, they're things that cluster. A lot of people study these clusters because they have some interesting properties associated with them. All right, so this is the sodium salt. Anyway, the potassium salt, and we end up forming NaHSO4. And what's the other product? Yeah, but well, we don't call it bi because there are multiple. If there's only one acid anion, we call it bi. But if they're multiple, then we call it like mono di. And so it would be potassium monohydrogen phosphate. And what's the formula for that? Yeah, K2HPO4. It's not balanced, but we don't care about balancing it until later. What we want to know is there a driving force? Because if there's no driving force, why bother balancing it? So, does sodium bisulfate precipitate? No, it's group 1 salt. Sodium salts are all soluble, so there's no precipitate there. How about potassium monohydrogen phosphate? Does that precipitate? No. It's also a group 1 salt. So no precipitate. Are either of those gases? Do you recognize those as gases, or salts are mostly solids, and a lot of them are soluble in water. Not all of them. So no gas. How about stronger to weaker acid? Now, monohydrogen phosphate is both an acid and a base. Monohydrogen phosphate is what we call amphoteric. Let's take a look at the acid chart here. And so when we look at monohydrogen phosphate, we see it here. And as far as on the left, what we have, the acids and the bases. Acid. And it's stronger than water, but weaker than, what do you call this? Bicarbonate. So stronger than water, weaker than bicarbonate. And then monohydrogen phosphate is also over here. And so it's also base. As far as base strength goes, is it stronger or weaker than ammonia? It's weaker than ammonia, but stronger than, what do you call this? How would you name that? The problem is there such thing as dihydrogen sulfide? Yes, there is, but we call it hydrogen sulfide. It's not an ion. And so in this case, there's only one acid anion. And so it would be hydrogen sulfide ion. This one would require ion, or bisulfide. This one you could call bisulfide. And so it looks like it's a better base than it is an acid. You see that? As far as ranking goes. And so it's a better base. So but it can go either way. And we don't know which way it's going to go until we see what it reacts with. All right, what about bisulfate? Bisulfate is actually a pretty good what? Acid, yeah. It's not a strong acid, but it's a pretty good weak acid. It's also a base. But when we look at the base properties of these are too weak to be really considered a base. All these, and so really bisulfate is just a weak acid. It could potentially act as a base, but it's too weak. Did you guys read the footnotes on the PowerPoint here? I should put the acid slide in this PowerPoint here. Too weak to be basic in water. So for example, chloride. Chloride's not really considered a base. And so if you have sodium chloride versus sodium hydroxide, there's a huge difference. Yes, chloride is a base on the chart, but there's a huge difference in strength. Chloride's so weak, we consider it neutral. It's too weak to be basic, whereas sodium hydroxide is a strong base. So, if you want to save money on antacid, you aren't going to do that buying, or getting salt packs from Chick-fil-A or someplace like that. It's not going to work because it's too weak to be basic. And so the same thing with bisulfate. Don't use sodium bisulfate to try to neutralize any stomach acid. However, you could potentially don't eat it. You could potentially use sodium bicarbonate. Sodium bicarbonate will neutralize acids.
I had kind of like a fun question about that topic specifically that I was thinking about. So sodium hydroxide, that's like drained, right?
Right.
Why? And stomach acid is
Hydrochloric acid and butyric acid.
You just like drink. Would it just make water and aqueous sodium chloride? But isn't it bad? Wouldn't they kill you?
Yeah, it'll kill you. But the problem is when it gets your stomach lining's constantly being eaten away, right, from the acid. But the cells, I guess, grow very fast. So you can maintain that, but your throat isn't like that. I mean, or your tongue, or your throat, or whatever else. That tissue is going to suffer severe damage. When you cough up that stomach acid into your throat, it burns severely. And so the same thing with sodium hydroxide. Sodium hydroxide will break apart. So sodium hydroxide will cause significant damage. Yeah.
Okay.
Don't do. So one of the reasons why people use sodium hydroxide in the drains is because it'll dissolve fats, and it will also dissolve hair, this kind of stuff, tissue, whatever. Sodium hydroxide you can use, and you'll learn this in organic chemistry. It can break certain types of bonds and reactions. When we're learning the chemical properties of sodium hydroxide here, we're looking at, what metathesis, what acid base, what redox. In organic chemistry, we look at, the molecules. And are there acid and base sites on the molecule that the sodium hydroxide can attack? And so this is why we want to understand things in terms of Lewis structure. All right, so no precipitate, no gas. No gas, no precipitate. What was the last one? Stronger to weaker acid. But when I look at this, I have monohydrogen phosphate. I still have monohydrogen phosphate. It didn't change. And I have a bisulfate. I still have bisulfate. And so no stronger acid to weaker acid. Therefore, what we say is that there's no reaction, NR. But is that the only kind of reaction we look for, metathesis? No. And so metathesis, there was no, I shouldn't say no reaction, right? Because I'm not considering all types of reactions. How many types of reactions are there? 3. And so I only considered one of the 3. So this is no, when I say no reaction, I should say no reaction for just did this yesterday. I should say no reaction for metathesis. All right, my computer has crashed, so, or this program has hung up, PowerPoint. I exit out of this. All right. So what we're going to do is we're going to look for other types of reactions that could occur. And so what other types of reactions are there? There's acid-base. And so let's try acid-base next. And so I'm going to try Bronsted next. Now the procedure for Bronsted acid-base is, the first step is we inventory. The major species. So sodium monohydrogen phosphate, aqueous, the major species in solution are going to be sodium ions and monohydrogen phosphate ions. And then potassium hydrogen sulfate, we're going to have potassium ions and bisulfate ions. And then there's one other major species, and that's the solvent. We have to watch out because the solvent can also react. Water is both an acid and a base. And there's potential for reaction there. And then we consult our chart. When we look at our chart, sodium does not appear. Sodium is not a hydrogen donor. There's no hydrogen on sodium to donate. And then sodium ions do not want to accept the hydrogen. You know, if I have a positive sodium and a positive hydrogen, have you ever seen this cation, NaH2 plus? There's nothing that's going to bond it together. So sodium's not going to be a proton acceptor. So in that case, we call it neutral, for it's neither an acid nor a base. Now, monohydrogen phosphate is both an acid and base, and we saw that it's a better base than it is an acid, but we still don't know. We still don't know how it's going to react because if, even though it's a better base than an acid, if there are no other acids around, then it's going to act as the acid. Potassium ions are also neutral like sodium ions. Now, bisulfate, the base is awful, but I'm still going to put it on there, but maybe I'll put a little asterisk here. I could ignore it because it's like chloride, it's so bad that it's not going to react in water. Okay, and then water is equally as comfortable as an acid as it is a base. It doesn't matter which way water goes, it goes both ways. So what we have to do is we have to use the chart to figure out what the strongest acid is. And if you recall, HPO4 2 minus wasn't that great of an acid, but it was still better than water. And if you recall, bisulfate it was borderline strong. It was near the top of the weak acids. So this is going to be the strongest acid. Then as far as bases go, this was the worst. Let's see. Let's compare monohydrogen phosphate with water and see which one was better. Let me do this here. These charts are kind of handy. And so I have them here, but I reuse these, so. But since this class is so small, you can have this if you want. That way you can don't have to print it out. So. All right, so take a look at the chart and see which is a better base, water or monohydrogen phosphate. Yes. So this is the better base here. And so that's what dictates, how we know how it's going to act is we compare it. We want the strongest species to react. And so we'll take the strongest acid, HSO4 minus, and react it with the strongest base, HPO4 2 minus. And we have to label it. This is going to be our acid, this is going to be our base, because both of these can be acids and both of these can be bases. And then we know the definition of Bronsted acid. What is the definition of Bronsted acid? Proton donor. And so the acid is going to donate an H+. So if bisulfate loses an H+, then it's going to form sulfate, SO4 2 minus. And if monohydrogen phosphate gains an H+, it's going to form dihydrogen phosphate. This is going to have a minus charge here. Now, could sulfate be amphoteric? It's impossible for sulfate to be amphoteric because there's no hydrogen to donate. And so the only thing sulfate can be is a base. And so we could label that as a base. Now, dihydrogen phosphate can be either an acid or a base, but in this particular case, what is it? It's an acid because what we do is we reverse the reaction. If we reverse the reaction, going backwards, sulfate gains a proton, dihydrogen phosphate loses a proton. And so going in the reverse direction, this is the acid, this is the base. That's how we determine it. And then we compare the two acids. Which of these two is stronger? That's going to tell us the downhill direction. The stronger one will be uphill, the weaker one will be downhill. So which is stronger? Bisulfate stronger. So this is stronger, this is weaker. So the downhill direction is forward. And that means we have driving force. Now we only have to look at the acid, or we only have to look at the base. Because if we did it correctly, because of the conjugate relationship, if it worked for the acids, it's got to work for the bases. So just let's confirm it. Are we going from a stronger base to a weaker base? That must mean monohydrogen phosphate must be a stronger base, and sulfate must be a weaker base. Is that correct?
Yeah.
Oh, yeah. Okay, then we did it correctly. And so we had no metathesis, but we did have reaction, and the reaction was Bronsted acid base. Here. Now, there's one more potential reaction that might occur, and what potential reaction should we consider last? There could be a potential. What's the third type of reaction? Oh, Lewis acid base. This is Bronsted. So I'll put that. But Lewis and Bronsted are the same. So if I get this, it's just when I can't get a Bronsted, I have to look at Lewis. So if I get a Bronsted here, I wouldn't bother looking at Lewis. And then I jump to redox. Okay. So there is a potential redox reaction maybe here. But we use a little bit of experience. Sulfates and phosphates are very common chemicals and somewhat stable. Let's go a little bit more here. Just do this one more, Bronsted. Or actually, let's try this. I'll leave this here for you guys to try. All right, we'll just take a break right now. Let's take a 10-minute break. And my PowerPoint hung up again. I have too much stuff open. If there's no Bronsted acid-base reaction, then there could potentially be a Lewis acid-base reaction. So when we look at Lewis acid-base reactions, we are looking for electron pair donor. This is our base here. And so it's going to have a lone pair. Ammonia has a lone pair here. And then we need an electron pair acceptor. In this case, it's going to be boron trifluoride. One thing I'd like to do that organic chemists don't do is I like to write the lone pairs here. Like that. And then ask, for example, here, BF3 has a lot more lone pairs. Why doesn't BF3 act as the base instead? Because each fluorine has 3 lone pairs, and nitrogen only has 1 lone pair. So just based on having a lot more lone pairs, it would appear as if BF3 would be a better base. If I don't write the lone pairs, of course, then I can ignore them, but let me make sure I started the recording. Well, they made it easy for us. They made it easy by not even bothering writing the lone pairs for the fluorine. That way you wouldn't get mixed up, right? But not everybody's going to make it easy for you. And so why is BF3 not the base? Well, it has to do with this. It has to, the more willing it is to donate the lone pair, the better. But willing, I mean, nitrogen is happy as is. 3 bond pairs, 1 lone pair. It's got the tetrahedral electron geometry, trigonal pyramidal molecular geometry. It's fine. And first off, fluorine is not good. Fluorine is not good is not as good of a lone pair donor because fluorine does not like to share its electrons. Because when we end up donating the lone pair, it ends up sharing the electrons, and it ends up forming a covalent bond. But in a normal covalent bond, 1 electron comes from 1 atom, another electron comes from another atom. So in a normal covalent bond, like this, fluorine forms a normal covalent bond. Fluorine has 7 valence electrons. And fluorine has no problem sharing in order to complete its octet. Yeah. And so this fluorine donates 1 electron here, this fluorine donates 1 electron here, and we end up forming fluorine, F2, molecular fluorine. But this situation is a little different. And therefore, we call this situation the coordinate covalent bond. In a coordinate covalent bond, both bonding electrons come from 1 species. So the nitrogen is going to donate both electrons for this particular bond. If nitrogen donates both electrons, then it's donating an electron to boron in this case. If nitrogen donates one of its electrons to boron, then it ends up with a positive charge over here. It's donated 1 electron. Over here, the formal charge on nitrogen is 0. Normally, we don't write 0 formal charges, but that's what it would be. And then essentially, boron is gaining that electron. So if boron gains an electron, it ends up with a negative formal charge here. And so that's the whole thing about the coordinate covalent bond. Both bonding electrons come from 1 species. We end up with this. Fluorine's not good because if fluorine donated both electrons, then essentially fluorine would end up with a positive formal charge like nitrogen. Does fluorine want a positive charge? No, because fluorine's the most electronegative element on the periodic table. So I wouldn't even consider these fluorines for donation, electron pair donation. Nitrogen, yeah, that could happen. We get something like this. This is like ammonium. Okay, so nitrogen's an okay donor. What about boron trifluoride here? Boron trifluoride, this is our acid, and acid is a electron pair acceptor. And boron trifluoride is a powerful Lewis acid, a strong acid. This is not one of the 7 common strong acids that you memorize. The 7 common strong acids you memorized were Bronsted acids. This is a strong Lewis acid. What makes this such a strong Lewis acid? Can you see it? Colin?
Like looking at the formal chart and the oxidation state on boron,
Yeah.
it looks like it has a 0 formal charge, which is like I think really is happy with that. But it has an oxidation state of like +3.
Yeah.
Which is really it's like pretty high.
It's pretty high, but boron is more on the left side of the periodic table, and so it has more metallic behavior. And so
it's more like that's more normal for it, right?
Yeah.
But then I just think of it as like in that center it's a very concentrated positive and around it it's very
Okay, that's true. This has got what we call positive charge density. Can you see it? Even though it's got a 0 formal charge, I look at that boron and I see that's what we call an electropositive atom. Electropositive means it's positive, so it wants to attract electron density, but it can't very well do that because fluorines are so electronegative. It's sucking all the electron density away from boron. So that's good. That would be correct. It is positive. It's being positive. The more positive it is, the better electron pair acceptor it is, because the more it wants negative electrons. And so that's good. And so that makes it a Lewis acid. But there's something else that makes it a Lewis acid. What is it? Can you see it? We expect it to be a Lewis acid. You know, it's fairly positive. However, it's very powerful because
Does it have to do with the bond it can form?
that has something to do with it. But there's something special about BF3. There's something special. This is if you recall, we should form a double bond here. Why should I take one of these lone pairs and make a double bond? To fulfill the octet rule, right? But I don't, because fluorine doesn't want to donate. If fluorine donated one of its lone pairs here, then boron could get an octet. But fluorine won't do that. Why?
It'll give it a formal charge.
Yeah, it'll give it a formal charge. So if fluorine decided to donate one of its lone pairs, so it only ends up with 2, then boron will be very happy, because now boron will have an octet. But this fluorine will be very unhappy, because it's essentially donating an electron to boron. The boron's gaining an electron, fluorine's losing that electron. Is that, if there's a tug of war for electrons, will boron win? No. Boron's not going to win. And so we can't get an octet on boron. And so this is what makes this a powerful Lewis acid, because it's got less than an octet. If you look over here, now boron has an octet. But fluorine didn't donate the electron. Who donated the electron? Nitrogen. And nitrogen, it's okay. And so the structure that we form is called an adduct. We form this. This is the coordinate covalent bond here. And this is our Lewis acid-base adduct structure. So at the very simplest level, the bases are going to be negative, and the acids are going to be positive. So when we look at molecules like this, we look for sites of reactivity. And the color coding system here goes like this. If it's red, it's negative. If it's blue, it's positive. And if it's green, it's kind of neutral. So these come from Spartan and programs similar to that, and it just maps out the electron cloud density around the atoms using molecular orbital type theory at different levels. And we can see, like blue would be positive. So those would be acidic sites, potential sites for electron pair acceptors. Red, as long as there's a lone pair, would be negative, and that could be potential sites for electron pair donors. And so when we look at our electron-rich areas, red, and electron-poor areas, blue. That's at a very rudimentary level. Then we have to look. These electron-rich areas must have electron pair. Must have an electron pair. If there's no electron pair, then it can't donate anything. And these electron-poor areas must be able to accept an electron pair. There's got to be room to accept. Like BF3 had room to accept because it was missing an octet. When we look at Lewis acid-base strength, and this is all Emma, when we form covalent bonds, we use molecular orbital theory for that. And the strength rankings are more complex than Bronsted. We don't have a simple table for that because it depends. Like sulfide. Sulfide would be a strong base for certain acids, but a weak base for other acids. Sulfide would be a strong base for soft acids, but it would be a weak base for hard acids. And so we have to use HSAB. What did HSAB stand for again?
Hard soft acid base.
Yeah, hard soft acid base theory. There's a whole Wikipedia section on this, if you're interested in looking.
Is there a way to tell which hard?
In general, small's hard, big is soft. Let's take a look at this one. Carbon dioxide is bubbled in water. This is the one I usually do. 1A. So the first thing is we need the Lewis structure for carbon dioxide. Since we don't have quantum mechanics, what we do is we just use bond polarity to kind of map out the electron cloud. So I'm not going to color code this. So the oxygens are electron rich, we'd say, because they're more polar. They're going to suck the electron density away from carbon. And so what I see is the delta negatives would be base, and the delta positive could potentially be acid. When I look at water, I should probably do more colors here. You can do the same thing here. The oxygen's delta minus, the hydrogens are delta plus. So this is a potential base site, these are potential acid sites here. When we do Lewis acid-base reactions, the base attacks the acid. And so we have two scenarios here. Scenario one is we could have this base attack this acid here. Now, MO theory is difficult, but it's more accurate. We need to use a simplified quantum mechanical version of bonding. And what is the more simplified version of bonding? We really should use MO theory, but it's too hard. Instead, we're going to use LCAO's MO. MO theory versus what theory? This is something you should review in Chem 1A. It's the quantum mechanical light version. MO theory is the quantum mechanical full version. The full version is a bit too much. And so we want to use the quantum mechanical light version, LITE version. Which one is the simplified one where we could do it with pencil and paper? MO is the LCAO. The other one is overlap of atomic orbitals. The overlap of atomic orbitals is called, rather than doing an LCAO, LCA is a full mixing of the atomic orbitals. So you take one atomic orbital on one atom, another atomic orbital on another atom, and then mix them to create new orbitals called molecular orbitals. You get the bonding molecular orbital and the anti-bonding orbital. But that's kind of complicated. So what we can do is a very simplified version where we retain the atomic orbitals and just overlap them. So bond is not the complete mixing, the LCAO of atomic orbitals. A bond is an overlap of one orbital with another orbital. It's called valence bond theory. And so for this, we like to use valence bond theory. And so describe the bonding here in terms of valence bond. What type of bond is the OH bond there in terms of valence bond theory? In terms of MO, it's kind of difficult. In terms of valence bond, it's not so difficult. What's the valence orbital on hydrogen? It's an s orbital, right? So hydrogen, we have an s orbital here. And then it's going to overlap with what orbital on oxygen? Well, what's the hybridization on oxygen? sp3. So on the oxygen, it's sp3 hybridized, so we're going to have an sp3 orbital here. And the bond is created by the overlap of an sp3 and an s. So this is called an sp3s sigma bond. sp3s sigma bond. You guys remember that stuff somewhat? If you're continuing on organic, then you have to have this stuff mastered. So if you don't remember it, maybe you'll never use it again, except for 1B. But so anyway, there are too many electrons. Can I overlap another? What's the hybridization on this oxygen? sp2. Can I take that sp2 lone pair and overlap it with the s orbital here? A bond is the overlap of 2 atomic. Can I put 3 atomic orbitals and overlap them like that? No, it's going to have too many bonds to the hydrogen. And so in scenario 1, this is the sequence. Oh, shoot. Can I undo that? So the sequence would go here. This sp2 lone pair attacks and overlaps the s. Now we got too many electrons there. So what has to happen is some electrons have to leave. And these sp3s electrons will leave. So the first step is the base here attacks this, and then it'll kick these electrons out here. You see, otherwise we're going to have too many electrons. Does that make sense? So if an sp2 comes in here, then these have got to leave. Those electrons are going to go to the oxygen. Okay. So the base attacks this acid in the form of this. This is scenario A. Scenario B will look like this. In scenario B, this base here will attack this acid here. And so we're going to have an sp3 lone pair. The sp3 lone pair is going to come here. But is there any place for it to go? Do you guys remember the double bond? This double bond is going to consist of what? One sigma and one pi bond. The sigma bond is going to be an sp2 sigma, and the pi bond is going to be pb pi. And what's going to happen is this is going to come here, but it's going to have to make room. The carbon has to make room. We can't have more than an octet on carbon. And so we aren't going to have 5 electron pairs there. And so what has to happen is some electrons are going to get kicked out. So these pp pi bonds are going to get kicked out, and it's going to create an sp3 lone pair. So it's going to rehybridize that oxygen. And so this is scenario B. And so we have 2 possible scenarios there, scenario A and then scenario B. It turns out that scenario A kind of dead ends. And then what we're going to do is we're going to pursue scenario B. So continuing with B, if this happens, then we're going to get something that's going to look like this. Water is going to come in like this and bond here. Now, what was once a lone pair is now a bonding pair. So here's an electron pair donor. That bond pair is converted, lone pair is converted into a bonding pair. We used to have a double bond over here. Now it's going to be a single bond, and this is going to have 3 lone pairs here. And then this is going to stay the same over here. Now, this is going to screw up all the bonding. And so what's going to result is we're going to get formal charges. So, for example, this oxygen is now going to have a negative formal charge. And this oxygen over here is now going to have a positive formal charge. This, if you look at this part, what does this remind you of? An oxygen with 3 bonds and a positive formal charge with 2 hydrogens or hydrogens stuck. What does that kind of look like? You know what it looks like to me? This part looks like hydronium, doesn't it? Hydronium. Hydronium is an acid, right? And so having this positive formal charge on the oxygen makes these protons extremely acidic. This is not like water. This doesn't look like water to me, or an alcohol. This looks like an acid. And what does this look like to you? This looks like hydroxide, except rather than having a hydrogen here, we have a carbon. So I have, when I look at this, I see a strong acid and a strong base. Do you see that? Bronsted. And so what can happen is, you know, these molecules and ions aren't static, they're vibrating. And so what can happen is a vibration can happen here. And if this sp3 lone pair here gets pushed into this S, it can potentially kick these out. Yellow's not good for contrast, is it? Go to orange. So these sp3 lone pair gets pushed into this S and it kicks these bonding electrons out like that. And then what forms? What forms is going to look like this. So we have this. This is H2CO3. H2CO3, what's that called? Carbonic acid. So this is the formation of carbonic acid. So carbon dioxide is bubbled in water. And so the overall reaction is CO2 plus water, H2O liquid, makes carbonic acid, H2CO3. This is a Lewis acid-base reaction. CO2, in this case, is the acid or the base in scenario B. In scenario B, CO2 acted as the acid or the base? As the acid. And water was the base. Now, carbonic acid is unstable, so this is not a very favorable reaction. This reaction is downhill in the opposite direction. This is the uphill. But how big of a hill is it to climb? Well, it's not terrible. That is, a little bit of the population of CO2 and water can make it up that hill. And so CO2 and water is a much more favorable combination here. CO2 gas, H2O liquid. It's not favorable because carbonic acid is less stable. But do you guys remember the Maxwell-Boltzmann distribution? Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution is the population versus energy. At 25 degrees C, if we plot the population versus the energy, are all water molecules moving at the same speed at 25 degrees C? No. Are all CO2 molecules moving at the same exact speed at 25 degrees C? No. What we see is a Maxwell-Boltzmann distribution of speed, energy. It looks like this. And there's going to be a small population of high energy molecules. This small population of high energy molecules out here has enough energy to climb this hill. And so that small population way out here in high energies can actually make carbonic acid. But the bulk of them, do they have that much energy? No, the bulk of the water molecules don't. And so we just have this tiny population that can make it up here. But the bulk of these molecules are down here. They can try to make it up the hill. So some of them can make it partway up and then fall back down. Some of them can make it farther, fall back down. So that's these guys here. they don't quite make it. And so the bulk of them are going to stay as CO2 and H2O. This is called a chemical equilibrium. A chemical equilibrium is a situation where we're going to have a steady state of these, because the carbonic acid doesn't stay up here forever. What's going to happen is the carbonic acid is going to immediately decompose. But what's going to happen next? Well, another energetic CO2 and another energetic water are going to collide and make another carbonic acid. Do you see that? And so what we end up with is a steady state. You know, the carbonic acid will drop back down, but as this drops back down, another pair climbs back up. And so we end up reaching an equilibrium state. In this equilibrium state, the concentrations don't change. This is called a dynamic equilibrium, because what happens is this constant up and down, but the net amounts of carbonic acid and CO2 and water don't change. Do you see that? Or not? And so, yeah, this is a very unfavorable reaction, but it can occur to a small extent if we have enough of this population of energetic species. The bulk of them are going to stay at the bottom here, and so this is why it's favored in the reverse. This is favored in the reverse direction. In Chem 1B, oops, forgot to duplicate this. Let me pause this here. Okay, let's resume that. All right, let's take a look at one more example here. How do you write the Lewis structure for ionic solid? So for the Lewis structure for ionic solid, I just like to make up the lattice. The Lewis symbols for ions would look like this. Calcium, which has no valence electrons, and we have oxide, which has an octet. And then we generate a lattice. A lattice is just the lattice of ions. This lattice is going to extend in 3 dimensions. So continues. And so this would be solid calcium oxide. Then we have water. And we have the same type of scenario that comes up here. Water can be an acid or a base. Calcium oxide is the same thing. In terms of calcium oxide, the calcium could be acidic or basic here. Acidic. And the oxide? Base. What do you think would be a better base? Oxide here or oxygen in water? What do you think would be a better base? Oxide or oxygen in water? Because oxygen in water, this is a base. This is our acid here. And when we think about acid-base reactions, the base attacks the acid. So which one would be a better base for attacking acid? The oxygen in water? Why is that?
Well, I feel like the oxides, calcium oxide, they're pretty, like, stuck.
It's stuck. It's stuck. It's stuck, but what we have to do is we have to rely on the water hitting it. So if the water hits the oxide versus the water hits the calcium, there's going to be a collision either way. The calcium's stuck also. Both are stuck. And so we have to react with the surface. It's like sugar cubes. When you dissolve a sugar cube in water, the surface gets attacked by the water. It slows things down, but eventually the sugar cube will dissolve. And so ignoring that because both of them are stuck, which one would be better? The oxide or the oxygen in water? What makes a good base? Good electron pair donor. And the electron pairs are negatively charged, so good negative, something that can donate negative charge. And so as far as that goes, oxide is the better base. Why? Oxide has a full -2 charge. What's the charge on oxygen and water? Delta minus. Delta minus means what? Partial charge. This is a partial charge. It's not a full charge. A full charge is an ion. And so this is just a partial. And so as far as base goes, oxide is going to be better base than.
So even though the oxygen is higher electron than hydrogen, because it's still sharing some with the hydrogen, it is less.
Yes.
Than oxide.
Right. It's less because electronegative is 2.1 for hydrogen. Oxygen is like a 3.5. And so it's like a electron versus calcium versus oxygen. Calcium's electronegativity is less than 1. And so it's a huge difference here. This oxygen is going to be a lot richer than this oxygen up here. The hydrogens are still in the tug of war, and it forms a polar covalent bond. Okay. So I'm just going to look at what I think is going to be the most favorable reaction. That is, if the water collides with the oxide, and so this sp3 lone pair gets pushed into this S. Now there are too many electrons, so these have got to get kicked out here. And so what we end up with is this. We end up with a hydroxide up here. And a hydroxide down here. And we have that calcium still over here. And so the reaction that I end up with here is calcium oxide solid plus water yields calcium hydroxide. Now calcium hydroxide, is that soluble or insoluble? Hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, and barium. So this is actually aqueous. I'll write aqueous here. And so this is going to end up dissolving. After it forms. So eventually the calcium oxide will react. All right, we'll do some more examples. I have some examples of this on the homework I posted on Canvas. So if we have no metathesis, no acid base, then I start looking for redox. And so let's take a look at redox, the different approaches in redox. One approach is a single replacement. The single replacement redox reactions follow this form. A plus Bs yields As plus B. There are places where you have to be careful with single replacement reactions. Single replacement, the advantage is it's easy. The disadvantage is that you could get the wrong answer. And therefore, you have to know where single replacement applies. It's like the ideal gas law. The advantage of the ideal gas law is it's easy. The disadvantage is you could get the wrong answer if you don't know where the ideal gas law is applicable and where it's not applicable. So for example, would you use the ideal gas law under conditions of very high pressure, let's say 100 atmospheres? No, because you're going to get the wrong answer. Would you use the ideal gas law under conditions of low temperature? No, it is likely you're going to get an error. And so you'd have to know, that ideal gas law works great under conditions of low pressure and high temperature. Single replacement works great if you don't have certain reactants. In Chem 4, it's easy because you just don't have to have those reactants. And so we could use single replacement if we restrict ourselves and we understand where it's applicable or where it's not applicable. But instead of using this, I prefer to use the chart method instead. As with the chart method, I can do all the single replacement reactions. It just takes a little longer. And I would get the correct answer, or a more likely to be correct answer. And sometimes we'll miss something, but it's just because our chart is not complete, or conditions are a little different. And so combustion is just combustion organics. This is already discussed. So single replacement is chapter 5 thing. Combustion, I think, was chapter 3. And so I'm going to spend my time talking about the chart method mostly. Skeleton reaction redox was chapter 5. And so let's take a look at the chart method here. I call it the chart method because we're going to use this chart. This is a redox chart. And this redox chart's from our book. This is from table 20.1. 20.1 of the 11th edition. And this chart is the selected standard reduction or electrode potentials. Okay. And this is similar to the acid-base chart. In the acid-base chart, on the left are the acids, on the right are the bases. There's a conjugate relationship between the acids and the bases. The stronger the acid, the weaker the base. It's conjugate. They have to be conjugate pairs. The stronger the base, the weaker the acid. Conjugate. Over here, what we do is we put our oxidizers on the left. And then on the right, we place our reducers. Now, that's not always the case. What if somebody decided, I want to put the bases on the left and the acids on the right? Is that okay? Yeah, that's okay because it's not a law. It's not a law or something that's more strict. They can put it wherever they want. And the same thing with these charts. A lot of people like to put the reducers on the left and they like to put lithium at the top. That's called the activity series. So the activity series is flipped. This chart flipped and then inverted kind of flips in a weird way, so the lithium's at the top. The strongest oxidizers are at the top left, and the weakest oxidizers are at the bottom. And the first thing is oxidizers. What do oxidizers want? Like oxygen. Oxygen is one of the best oxidizers around, and what does oxygen want? Why do we call oxygen a good oxidizer? A lot of people take antioxidants because of oxidizers, potential oxidizers. To lose electrons? Oxidizers don't want to lose electrons. The opposite. Oxidizers want to take electrons. Yeah. Oxidizers take electrons. They take electrons from what? Well, if oxidizers take electrons, then who loses electrons? Reducers. Reducers lose electrons. So up here is fluorine. Fluorine's the strongest oxidizer on this chart. And fluorine is going to take electrons from most other species. Once fluorine has taken those electrons, it forms fluoride, its conjugate. Fluoride doesn't want to lose those electrons, so fluoride is going to be the weakest reducer because it does not want to lose electrons. Whereas strong reducers can have a tendency to easily lose electrons. So for example, lithium. Lithium easily loses electrons, and therefore it's a strong reducer. Potassium, etc. These all have very low ionization energies. Fluoride, on the other hand, is extremely high ionization energies. So the chart method is very similar to the Bronsted. We inventory, we find the strongest oxidizer, we find the strongest reducer, and then we react them. We're going to be using this chart. So once in a while we go through, what are the strong oxidizers? Fluorine, ozone, strong oxidizer. This one, which looks like bisulfate, but it's not called bisulfate. This is a peroxide. This is strong oxidizer. Hydrogen peroxide is a strong oxidizer. Permanganate. Why is permanganate a strong oxidizer? Permanganate has a negative charge. Why does it want more negative charge? Can somebody tell me why permanganate is a strong oxidizer? Permanganate is number 1, 2, 3, 4, 5. It's number 5 on the chart. Why is permanganate a powerful oxidizer?
Is it because manganese has a super high oxidation state?
Yes. Manganese has a super high oxidation state. What is the super high oxidation state on manganese? +7. +7 is electron poor, we call that. In fact, +7 is its max on manganese, max count. And so this is electron poor. It's not electron rich. That negative charge belongs to oxygen. Oxygen's happy with it. So once in a while we read through these. Metals are great reducers. Metals tend to lose electrons. Some metals aren't so great: copper, silver, platinum. And then there are other species that can also lose electrons. So basically, we're just going to use the chart. We don't have to understand the theory behind the chart. We just need to use the chart. Using the chart is not too difficult. So we can use the chart in different ways. If two fluorines got in a tug of war for electrons, which fluorine would win? It would be a tie. So what we need is we need either a stronger oxidizer or a stronger reducer. You know? And so the same thing can happen here. I asked you one of the chemical properties of HCl. Well, HCl contains H+. If H and H got into a tug of war for electrons, who would win? It'd be a tie. So what we need is we either need a stronger reducer than hydrogen, or we need a stronger oxidizer than H plus in order to get it to react. And so these metals here, do you know what we call these metals that are below hydrogen? The metals that are stronger reducer than hydrogen are given a name. The metals that are stronger reducer than hydrogen are called the active metals. The active metals will all react with acid, H plus. So for example, if I have H plus and aluminum, the aluminum gets converted into aluminum ion. So we're going from a stronger oxidizer to a weaker oxidizer, aluminum ion. And the H plus gets converted to hydrogen. So we're going from a stronger reducer, aluminum, to a weaker reducer, hydrogen. And so this works out. It's downhill this way on the left, and it's downhill this way on the right. However, if I try to go uphill, it doesn't react. So for example, HCl does not react with copper because that would be uphill. So if I tried to get H plus to attack copper, what would I form? I'd form copper 2 plus. Well, copper 2 plus, that's uphill. That's not favorable. And I'd form H2 gas. H2 gas, that's uphill. On the right, uphill is down. And so that's not favorable. Do you see that? So these are the ways we use these charts here. So when we look at chemical properties, we could look at it individually. You know, does HCl react with aluminum? Yes. Or we could look at it collectively. HCl will attack any metal that's a better reducer than hydrogen. Do you see the two ways we look at chemical properties there? All right, let's go back to the chart method here. We combine the strongest oxidizer, half reaction, with the strongest reducer, half reaction, making sure that the number of electrons consumed is equal to the number of electrons lost by changing the coefficients if necessary. And then we simplify, and then we determine driving force. Okay, when we do this method, it yields the net ionic equation. So let's just get some practice with this method here. We're going to do copper and nitric acid here. When I say copper, is that Cu, Cu plus, or Cu2 plus?
Cu solid.
It's Cu solid. Plus nitric acid, what's the formula for nitric acid? This one looks like an A plus Bx pattern. The A plus Bx pattern yields Ax plus B. So Ax would be copper with nitrate. What's more common, copper 1 nitrate or copper 2 nitrate? Copper 2. And B is hydrogen, so that would just be the element hydrogen, H2 gas. What's the driving force for this? Is the driving force gas formation? And the answer is no. This is driving force for metathesis. In redox, we have a different driving force. And so in single replacement, the driving force is going from more active to less active. And so in terms of the activity series, we have it. Let me show you the activity series. This is an upside down activity series here. So if we look at our upside down activity series, lithium is the most active. And then here's hydrogen, and there's copper. Which one's more active, hydrogen or copper? Hydrogen. Lithium's the most active. That means hydrogen is more active than copper. And so hydrogen is more active. Copper is less active. Do you see this is uphill? The downhill direction is reverse. The driving force is reverse. Therefore, no reaction, NR. No reaction. However, this is correct for single replacement, but it turns out it's wrong for redox. There is a redox reaction here. And so this is wrong. There is redox. And so, do you see the pattern? No. Redox is more complicated.
So to summarize, there's no reaction, but there is redox.
Single replacement fails. Well, it doesn't entirely fail because there is no single replacement reaction. But it does fail because single replacement makes certain assumptions. And so I'm just going to say single replacement fails. One, you can memorize all the failures of single replacement so that you can avoid those in the future. Or two, you could just use the chart method. I've memorized all the failures for single replacement. I don't know if you want to do that. It's not so difficult. This is a common failure for single replacement. The common failure for single replacement is HNO3 here. HNO3 is not a normal acid. HNO3 is different than HCl. HCl is a normal acid. HCl is a normal acid because one of the properties of all acids are oxidizers. Did you know that? All acids are oxidizers. Why are all acids oxidizers? Because all acids contain what? All acids contain well, how do you recognize? Well, all Bronsted acids. Let me just, I have to be careful. All Bronsted acids are proton donors, and all Bronsted acids contain hydrogen. H plus is proton there. And therefore, H plus is a oxidizer. It's a moderate oxidizer. It's in the middle, kind of, right? And so all acids are moderate oxidizers because all acids contain H plus. All acids can eat up metals like this, the active metals. And these super reactive metals can be attacked by water. Water is acidic enough to attack those. Or, no, I shouldn't say acidic. I should say a strong enough oxidizer to attack those. But there are some special acids. These special acids would start with sulfuric acid. Sulfuric acid is a combination of sulfate and H plus. And then to go to nitric acid. Nitric acid is a combination of nitrate and H plus. Those are called oxidizing acids. They're called oxidizing acids because they have extra oxidizing ability. The extra oxidizing ability comes from the anion. And so we got to look at the anion. If the anion is electron rich or electron poor. In this case, sulfate's electron poor. Sulfur has an oxidation state of +6. Nitrate's electron poor. Nitrogen has an oxidation state of +5. Those are oxidizing acids. So nitric acid can attack a lot more species than hydrochloric acid. Can you see that? Nitric acid can attack all the reducing agents stronger than this. So nitric acid can actually attack silver. Hydrochloric acid won't touch silver. It's uphill. But for nitric acid, that's downhill. Nitric acid can eat up copper. Hydrochloric acid can't. Hydrochloric acid, that's uphill. For nitric acid, that's downhill. You see that? So nitric acid is a special acid. So when we have a special acid, we cannot use single replacement. And then there are other exceptions. But, you know, instead of memorizing the exceptions, we have an alternate method. And the alternate method is called the chart method. Now, the chart method isn't really discussed in the book as a separate section. The chart method is talked about in conjunction with batteries. And I don't want to talk about batteries yet. And so I just want to talk about the chart method now. And it's in chapter 20 or so. The chart method is not difficult. Anybody could do it. You don't need to know theory. You don't need to know valence bond theory, MO theory, none of that. And so we're just going to use the chart method. So the chart method, we inventory. So copper is not a strong electrolyte. That just stays alone. But nitric acid is. And so nitric acid is going to break apart into H plus and nitrate. And then we have one more species, and that's water. Water, surprisingly, can be oxidized, and it can oxidize other things. Water can participate in redox reactions as well. And so these are the species present. And then we just consult the chart. Do we find copper on the chart? So we look at the chart and we look for copper. Do you see copper metal? What side is it on? The left side or the right side? It's on the right side. The right side are the reducers or the oxidizers? Reducers. So I'm going to label copper here Ra. R stands for reducing, A stands for agent. So Ra is reducing agent. So copper is a reducer. Then look for H plus. Is H plus on the left side or the right side? And so H plus is an oxidizer, and so we call it an OA. Nitrate, left side or right side? Left side, so that's also an OA. However, nitrate is special because we need one more thing. When we look at the equation there, it's 1 nitrate plus how many H pluses? Plus 4 H pluses. So nitrate requires H plus. If we don't have H plus, then it doesn't quite work. The H pluses are crucial because if the H pluses aren't present, then we aren't going to form what product on the right. What product is H plus used to make? Water. Water's stable, and that helps this go. If we don't have H pluses, it forms oxide, and oxide is not stable. Oxide is a pretty powerful base. And then water, what side does water occur on? The left side or the right side? Left side. Do you see it's at the bottom left? If it's at the bottom left, does it mean that it's the worst oxidizer? No, it doesn't. There are two charts there. you have to position water based on the number on the right. So what is the number on the right side? Do you see it? The number is negative 0.828. And so water is positioned, now look at the numbers on the right. Where would you position water relative to the upper chart? Negative 8.28 means that water goes in between negative 0.44, negative 0.7, or no, negative 0.763 and negative 1.6. Do you see that? So it goes between zinc ion and aluminum ion. So what that means is water is a better oxidizer than aluminum ion, but a worse oxidizer than zinc ion. That's where we position it. And so on this chart, do you see the 3 dots I put on the chart between zinc and aluminum ions? That is where you insert water. Okay, so it occurs on the left side, and it occurs on the right side. When I look at the right side, I see it twice. Do you see it? Look at plus 2.075. Oh, no. If I go to plus 2.075, I can't use that. Why? Because I'm missing something. What am I missing? Oxygen. However, if I go to plus 1.763, there it is. Do you see it? But when I look at plus 1.763, I can keep going down, and then I see it again at plus 1.229. So which one should I use? Should I use the 1.763 or should I use the 1.229? And the answer is use the stronger of the two. Which one's stronger? Now the stronger means, well, it means where's the strongest reducer? Is it at the top or the bottom? At the bottom. And so I'm going to use the 1.229. That's stronger. And so that's the one we'll use. And then it turns out that water is both an oxidizer and a reducer. So we have 3 oxidizers and 2 reducers. Out of the 3 oxidizers, which one's the strongest? Nitrate and H+. So out of the 3 oxidizers, nitrate and H+ is the strongest, so we'll ignore the other 2. Out of the 2 reducers, which one's the strongest? Copper. So we'll use copper. So in the next step, what we're going to do is we're going to copy the reactions there. Those are called half reactions. And so we're going to have nitrate plus 4H plus 3 electrons yields NO gas plus 2 H2O liquids. So this is called a half reaction for the nitrate. And then for copper, we have to flip it backwards because copper is not our product. Copper is our reactant. And so if we flip it backwards, we end up with copper solid goes to copper 2 plus 2 electrons. This is our other half reaction. And so we'll have our reactants there. Okay, the next thing we look at are the electrons here. Over here, I have to gain 3 electrons. Over here, I have to lose 2 electrons. It's not balanced. So what we have to do is we have to balance out the electrons. The way we balance out the electrons is we multiply. The common factor would be 6. So I'm going to multiply the top one by 2. That's going to give me 6 electrons here. And then the bottom one I'm going to multiply by 3. So I end up with 6 electrons. So I have 6 electrons on the top one, 6 electrons on the bottom one, and that's what we say it's balanced electronically. Then. Okay, then the next thing to do is we're going to add these, what I need to make sure is I need to make sure that the electrons cancel. So I have 6 electrons being consumed here and 6 electrons being produced here. The electrons must cancel. And so that's why I end up multiplying. So I'm going to get 2 nitrates. Does anything else cancel? No. Plus 8H plus 3 coppers. I'm going to add everything on the left. And then I'm going to add everything on the right. This is going to go to 2NO gas plus 4H2O liquid plus 3 copper ions. Okay, then I look for driving force. For driving force, I like to use the conjugate relationship. And the conjugate relationship is going to be like this. This was our oxidizing agent in the forward direction. It was nitrate and H+. This is our reducing agent in the forward direction. So if this is our oxidizing agent, I look at the half reactions, and this is the conjugate reducing agent over here. So this is my conjugate reducing agent. So NO and H2O, that's my reducing agent. Okay, nitrate and H+, that's my oxidizing agent. Copper metal, that's my reducing agent. And then copper 2 ions, this will be the conjugate oxidizing agent. We have pairs. So OA, RA, RA, OA. And so this will be our OA here. And then what we do is we compare what's better oxidizer, nitrate and H+ or copper 2 ions? Nitrate. So we just consult the chart. And so this is stronger, this is weaker. Because of the conjugate relationship, it must mean that copper is a stronger reducing agent than nitric oxide, nitrogen monoxide, and water. And so we have driving force here. So nitric acid will dissolve copper metal. In single replacement, it did not predict that. In this, it does predict it. Now, NO gas is colorless. And so what happens after this is the NO gas reacts with oxygen in air to form NO2 gas. This is orange-brown gas, or it's an orange gas. This is a colorless gas. This happens spontaneously. And so there's a secondary reaction here that occurs. This is also a redox reaction as well. So we could see this reaction here. I don't know if the audio works in this one. Probably doesn't.
In Key Stage 3 and 4, students perform experiments that series so that you can later on develop this.
All right, so you can't even see it, can you? You see it? Well, it's not coming up. Here's that. I'm not sure if my webcam is working over here.
This is Lonnie's lab at UC Berkeley. We're in the demo lab to see Lonnie oxidize copper metal, oxidation state 0, to copper ions, oxidation state +2. The oxidizing agent will be nitric acid, NO3 minus. NO3 minus will be reduced to NO2. NO2 is a brown gas you'll see immediately start to form when the nitric acid comes in contact with the copper metal. Now, copper ions, C+2, are blue. So Lonnie can add some water to this mixture, and we'll see the lovely blue color of the copper ions and the brown gas, NO2, formed above them in this oxidation reduction reaction.
So it reacts quite vigorously there.
These are my notebooks. So understand.
I can go back to. Okay. I thought I resolved it, but. I see what happened. All right, we'll look at reactions again next week. What I want to do here is, or actually tomorrow as well, but I want to take a look at chapter 24. And I have these on Canvas, lecture notes, PDF. And so I downloaded that here. So I want to talk about the complex ions and coordination compounds, just complexes in general. We're going to just cover these first three sections. Werner's, ligand, nomenclature. I don't really focus on nomenclature. Here's turquoise. Turquoise, you look at the structure like this, it looks like some ionic compound, some hydrated ionic compound. And when we look at the structure more deeply, it forms what we call coordination complexes, or complex. And so what is that? Well, let's go back in history here and look at Werner. This is Werner here. Werner won the Nobel Prize for his structural studies on these. So first off, let's take a look at these cobalt-3 chloride. Cobalt-3 chloride is an ionic compound, and ammonia is a molecular compound. And hydrates, when we look at a hydrate like this, .4H2O, what does that mean? So if we have this ionic compound, .4H2O, that means that it's dissolved in water. Turquoise dissolved in water. Where do the waters go in a hydrate? Yeah, it gets absorbed into the lattice. So does turquoise look wet to you? It doesn't look wet to me, but those waters are stuck in the lattice. Now, I could dehydrate turquoise. How would you dehydrate turquoise? Yeah, just throw it in the oven and heat it up until the water gets forced out. Okay? And so it doesn't look wet, but this is a hydrate, and that's what we expect. And so the same thing, ammonia is a polar molecule, just like water. Ammonia in certain ways is very like water because it can hydrogen bond and that kind of stuff. So these are like hydrates. I can stick different amounts of ammonia into the crystal. What if I want to de-ammoniate it? That is, just drive off the ammonia. I just throw it in the oven and heat it up until the ammonia gets driven off as a gas. Ammonia is normally gas. But these ammonias are stuck in the lattice here. And so one of the things is it depends on how much ammonia gets stuck in there. And so it could be like a hydrate could be fully hydrated or partially hydrated. And so it looks like 4 is the max, and that would be fully hydrated. But maybe I could throw 3 in there. Maybe 3 waters of hydrate might change the color, or 2 waters of hydrate. We can see this, like these color changes in dehydrated versus hydrated forms of copper 2 sulfate. Maybe that'll come in. The hydrated form is very nice. This would be the hydrated here. This would be the dehydrated form, or the anhydrous form. The dehydrated has just a very light blue color. So, hydrated. There's something in between, I think. There. Here you can see the dehydrated form, which looks white and parched, versus the hydrated form, which is this dark blue color here. So, here, actually, it didn't. The ammonias would be acting like waters of, in a hydrate. But there are some unusual behavior. So the color is one thing. They definitely have a distinctive color depending on how many ammonias you can stick in there. But there's one more thing that was a bit off. And so let me show. And that's this. Okay, so if the ammonias are just stuck in the crystal lattice, they're in between like the cobalts and the chlorides, they're probably in some void space, interstitial space, we call it, or void. And so if we take this solid, chlorides are all soluble in water, except for silver, mercury, and lead. And so we'll just dissolve this in H2O. And when we do that, it's going to break apart. And so the lattice breaks apart, and we end up ionizing it. And so we should form cobalt-3 plus 3 chlorides. And then the ammonias will be free from wherever they were trapped in the crystal structure. Ammonia is very soluble in water, so they'll just be aqueous. And we'll just form the aqueous species like this. If we look at cobalt chloride with 5 ammonia stuck in the lattice, this is water soluble as well. And the inventory of species we're going to get would be cobalt-3, 3 chlorides, plus 5 ammonias. So one of the spaces is empty in the lattice. And so this is capable of absorbing 1 more ammonia. If it absorbs 1 more ammonia, we get 6 ammonias in there, and it changes the color like this. This is it. All right, so when we do that, then how can we test this? You know, is there a chemical property that we can use to test for any of these species in solution? Do you know? One thing we could test for is ammonia. Another thing we could test for is chloride. And so if we think about HCl, HCl consists of two things, H plus and Cl minus. H plus has properties, Cl minus also has properties. Can you tell me some properties, chemical properties of Cl minus? What are the chemical properties of Cl minus? If I ask you what the chemical properties of Cl minus are, chloride, you'd look at metathesis properties, acid base, and redox. Acid base properties, chloride is so weak, we don't really consider it a base. And so as far as Bronsted acid base, chloride's pretty unreactive. We call it neutral. But what about metathesis properties for chloride? Do you know what ions chloride likes? Silver. And so what we can do here is we can continue this on here. And so that is, what we're going to do is for this one, we'll just continue it over here. And then we're going to add silver chloride, excess. And so what do we expect? If I add excess silver, I can't add silver chloride. Silver chloride's insoluble. I have to add silver nitrate. Nitrates are soluble. So if I add excess silver nitrate, the silver ions will attack the chloride, and I should precipitate out 3 moles of silver chloride. Does that make sense? All right. If I do the second one, will I get the same amount of silver chloride? So I add excess silver nitrate. How many moles would I expect from the penta ammonia versus the hexa ammonia? Would I expect the same amount of silver chloride in both of these? Well, how many moles of chloride do I have in the first one? 3. How many moles of chloride do I have in the second one? 3. And so actually I would expect the second one to yield 3 moles of silver chloride. So we can't tell the difference using silver chloride, could we? No, we can't tell the difference. We could tell the difference using ammonia because we have different amounts of ammonia. So we need a test for ammonia, quantitative test for ammonia to figure it out. But do you know what the weird thing was? This was what was expected. Do you know how much silver chloride they observed for the hexa? 3. And so as far as observed goes, this checks out. But for the penta, we expected 3, but only observed 2. So no matter how many times this was repeated, only 2 moles of silver chloride would precipitate for every mole of cobalt-3 chloride, penta ammonia. So something's wrong with our structural understanding of this. The ammonias aren't just trapped in void spaces. Do you guys remember the different kinds of void spaces we had in crystals? The octahedral, the tetrahedral voids. They aren't trapped in those void spaces. Something else is going on. So to make a long story short, there's something else that's going on is that there's more complex structure in there. And what's going on in the hexas, the cobalts are actually bonded with the ammonias. The ammonias just aren't stuck in there. And so what we have here is we have a Lewis acid-base reaction. with the ammonia. So the cobalt is in the lattice like this. But what happens is the ammonia is actually a pretty good Lewis acid or Lewis base. Yeah, the ammonia turns out to be a pretty good Lewis base. And so what happens is the ammonia attacks the cobalt. And when that happens, we end up with a coordinate covalent bond. And so the ammonia is not just stuck in the lattice, the ammonia is actually bonded to the cobalt. Like this. Now for complexes, we don't do formal charge. For complexes, valence bond theory fails. So we don't do the usual stuff we do with valence bond theory. And so here we don't worry about Vesper. Vesper is part of valence bond theory. And so we don't use Vesper. And formal charges we don't count in the same way. We have to use MO theory for complexes. And so we don't think of this in the normal way. So normally, if I have nitrogen with 4 bonds, what's the formal charge on nitrogen? Like in ammonium. Normally, this nitrogen would have a positive formal charge. And then the cobalt 3 would go to cobalt 2+. This is what we normally do. But for complexes, we don't do things in a normal way. So for a complex, this is what we're going to do. The cobalt is going to stay at 3+. And the ammonia is going to stay neutral. Like that. And so this is what's happening. And so what's happening is the ammonia is actually bonding to the cobalt. And so this is what's screwing up our understanding. It's not an ammonia that's stuck in the lattice. Okay, we're out of time here, so I'll stop here and continue tomorrow.